Alright everybody, and now welcome to Investigation 8B. So, in the previous investigation we talked about wind forces at the surface of the Earth. Now we're going to talk about winds in the upper levels of the atmosphere. So, we talked about surface winds, now we're going to talk about upper level winds. And so, for this lab, the first thing we're going to do is we're going to differentiate surface winds from upper air winds. Then I'm going to show you how to read an upper air station model. And then we're going to determine patterns in the upper air wind, such as troughs and ridges. So here's the first thing that you need to know about the upper layers of the troposphere. Here at the surface, when we do a surface wind map or a surface map, we do it at sea level. So we take everything and we calibrate it to sea level. This isn't the same thing in the rest of the atmosphere. At different elevations in the atmosphere, we are actually going to break the wind, we are actually going to be looking at different pressure levels. And so all upper air maps, rather than being done for a constant elevation, they're being done for a constant pressure level. So for example, there are maps for the 750 millibar level, the 500 millibar level, the 300 millibar level, and the 200 millibar level. And the reason why we do this is that each of these elevations, each of these pressure levels actually has different features that we want to know about. Such as the 750 millibar level is where we look at advection, which is just a fancy word for movement of air. On the other hand, the 500 millibar level is where we go to begin looking at the jet stream and looking at troughs and ridges. And in fact, we actually look even further up at the 300 millibar level to get a larger scale picture of the jet stream. So we look at individual pressure levels. Now with that said, the maps that you're going to see actually look very similar to maps that you saw on the surface of the Earth. And there's not a whole lot that's different. So the same station models that are used on the surface of the Earth are almost exactly the same in the upper atmosphere. There's a couple of things that are different. All right, so here's what you need to know. First off, here on the left side, air temperature and dew point temperature are located in the same place they were for surface maps. Upper left for temperature, lower left for dew point. The only difference here is that they're actually given in Celsius rather than Fahrenheit. And the main reason why is because these maps are used primarily by operational meteorologists who work in Celsius. The next thing to know, there is no worry about precipitation or cloud cover at these individual heights. So we don't actually do those. So there's no cloud cover, no precipitation. What there is, though, is a wind barb. And this wind barb works the exact same way as it did at the surface. It points in the direction that the wind is coming from. It has the same cardinal directions: north on the top, south on the bottom, west on the left, east on the right, just like surface maps. And the individual barbs themselves are also the same as on the surface of the Earth. One feather means 5 knots, one long feather means 10 knots. The only thing that might be different is the winds near the surface don't get nearly as strong, and so you might not have yet seen this pennant right here. Actually, let me pull up my laser pointer. This pennant right here, which that actually represents 50 knots. And so adding these up, you have 5, 15, and then this is worth 50, so that's 65 knots. Now the very last thing that is different is, if you remember at the surface, this 3-digit number was actually the last 3 digits of air pressure. That's not the case here. Everywhere on this map is at the same pressure. Rather than using a constant elevation, we're using a constant pressure level. And what this number instead tells us is how high up was the pressure level at that location. So for example, this number here, 549, this actually represents it. They do it in tens of meters. So basically they just drop the 0 at the end. And so 549 is just 5490. So this location is 5,490 meters above the surface of the Earth. And so that's where the 500 millibar level is located, or so on. And there's actually a table in the manual that actually goes through each of the different levels and what this upper right number means. With that said, we're going to primarily be looking at 500, 300, and 200 millibar maps. And in all three of those cases, it just means take this, put a 0 at the end of it, and you're good to go. So that's all you need to know for upper air station models. Now with that said, these station models are actually collected or actually measured using weather balloon launches. And then once we get those weather balloon launches, we then collect all the data and put together an upper air map. And this is actually the upper air map that you'll be looking at for this assignment. So I'm not giving you something different here. This is actually the map that you're going to be looking at. And let me tell you what's going on here. So first off, these blue lines, these are what are called height lines. They actually represent a constant height rather than a constant pressure level. However, they actually read and work the same way that isobars on the surface of the Earth work. If they're closer together, the winds are going to be stronger. If they're farther apart, the winds are going to be weaker. And I mean, a good example of that is right over here, over Utah, Colorado, and Wyoming, where these height lines are pretty close to each other, and the winds are a lot stronger. Whereas down here, over southern Texas and southern Louisiana, the height lines are much further apart, and therefore the winds are a lot weaker. Now here's the other thing that you need to know. These lines also give us a really good sense of a pattern called the jet stream, which we'll actually talk about in the next assignment. And the way that the jet stream works is there are different components to the jet stream. And the components are called troughs and ridges. And a trough, like this one right here, is what happens when these height lines begin to form what looks like a U shape. Kind of like this. This represents a depression, an area of lower pressure and colder air. And so that's what a trough looks like. And so we see this pretty big trough over the western United States. Meanwhile, if you notice on the other side of the United States, there's actually what looks like a large area of where this actually begins to take on a little bit more of a ridge type shape to it. It actually looks more like a small hill. Well, these are called ridges. And these typically represent areas of warmer air, of higher pressure, of typically they tend to represent warmer air. And if you remember from the block analogy that we did a few labs ago, warmer air ends up resulting in higher heights. Warmer air stretches out longer, it creates a taller stack of blocks. And so that's what's happening over here. So that's what this ridge over here is. Now the last thing I'll talk about are these height lines, and there's a few important things to note here. If you actually notice, for the most part, as you're traveling from south, down here, up to north, what are the value of these height lines doing? Well, if you notice, this lowest one was 5820, then 5760, 5700, 5640, 5580, and keep going up. Basically what's happening is, as you're increasing in latitude, meaning getting further away from the equator, what's actually happening is that these heights are decreasing. And that might sound a little odd, but there's actually some rhyme to the reason. So here's what's actually happening. Near the equator, the air is really warm. Well, again, think of that stack of blocks. The warmer air leads to a taller stack of blocks, meaning the heights are going to be higher. So warm air means higher heights, and some of the warmest air on Earth is down near the equator and over some of the larger deserts, but let's not worry about that right now. On the other hand, as you move away from the equator, you're getting less heat, less energy, therefore you're also getting lower heights. So as you travel towards the pole, the heights in general are declining. So you're going from 5820 down here, all the way down to, I see 5280 all the way up here. Now be careful with that though. You're going to be asked which station has the lowest height. We're not talking about the the height lines, these height contours. We're actually talking about the reported number at the station model. So look around the station models, identify where the highest height is and where the lowest height is. And I'll just give you a hint. Highest height, probably somewhere down here. Lowest height, quite possibly somewhere up here. And another good thing to think about, you're likely to find the lowest height usually near a trough. So that's really all that you need to know for this particular assignment. Now, I actually recommend, if you're doing this assignment, I would actually recommend once you finish it, jump right into the next assignment, because what we're going to be talking about there is very similar to what we just talked about right now. So once you're done with this assignment, I say get up, go grab yourself something to drink, take a deep breath, and then come back and do the next assignment, Investigation 9A, which covers the jet stream.